Okay, so now we will continue on our topic regarding the finite difference method for solving the BVP. The finite difference method for solving the BVP. BVP. The finite difference method. The finite difference. We can call it type D method. Essentially converts ODE into number of the linear algebra equations into a couple set of algebra equations. And we will use one balance equations for each finite difference node or volume. Okay. One balance equations for each finite volume or node in the system. So the finite difference method is different as the shooting method. Shooting method, basically you give the initial guess of the missing conditions of the initial condition, then you solve the BVP as IVP. But the finite difference is basically convert that unsolved ODE into n different linear algebra equations and using the balanced equations for each finite volume or finite node. And we will show how we can write the ODE into algebra equations. Okay, the general type of FD is to replace the continuous ODE. Okay, to replace continuous derivative within the ODE with finite difference approximation on a grid of match points that spans the entire domain. Okay. So basically our ODE is a continuous differential equations, right? It's represent the continuous derivative. But for the finite difference approximation is that instead of writing a continuous derivative, we use we use algebra equations on a grid of the match points that spans from basically from x0 to xf. And we will treat the boundary points differently. Treat boundary points different. Okay. And we will first introduce what kind of finite difference approximation we will use. Then we will show how we can convert the ODE into the finite difference approximation. Okay. So first we will show what kind of finite difference method we will use. Okay. The finite difference method. We will show 2 points BVP for second order ODE. Okay. Instead of shooting method, how we use the finite difference method. The second order ODE we can write as y double prime minus plus p. Y double prime will be equals to dpxy prime plus qxy plus the forcing function, okay, where the x is in the range between 0 to b. Okay, this is the range of x. This is the second order ODE. Okay, the boundary conditions, we will use the direct directlet boundary conditions, which is only as function of y. So ya at point A. Okay, so this is x over a smaller than b in the range. So at the initial point, we give initial value alpha. At the final points, we give initial value at beta. Final condition is beta. So this is a boundary conditions. Means that the conditions are passing more than two or two more points. Okay. Then the grade of this created point, or you can say the mesh grades you will use for the finite difference method, will be only at this point xi. Okay, only at xi. And what is this xi? Will be b minus a divided by n, means you have n points in between a and b, between your initial and final points, and this xi will be a plus ih basically, and this I will be start from 0, 1 until your final points n, right? So that it range from the initial to the final points. Okay, and you are trying to seek yn, basically your final points will be y at xn, okay, approximately. And you know y at x equals n will be equals to beta. So you are seeking some points at this final point equals to beta. And for the finite difference approximation, for the derivative, so we already know the finite difference method is replacing the continuous ODE with the finite difference approximations over from x0 to x final, using this FD approximations and writing as a discrete format instead of the continuous derivatives. So for the finite difference approximation, using different finite difference approximation, it will lead to different FD method. Let's see, for the first derivative, we can have f prime equals to fx plus h minus fx divided by h. And this is called the forward-Euler method. Forward-Euler. Okay. So this is one of the finite difference approximation. And we also can have, for the first derivative, we can also write as fx minus fx minus h divided by h. This is called backward-Euler. Okay. So there are different approximations for the finite difference. We can also have, for example, fx prime equals to fx plus h minus fx minus h divided by 2h. And this is called central finite difference. Okay. And for this h has to be very small, so that your finite difference method is accurate. So for the first derivative, we already have three different methods. It can be forward-Euler, backward-Euler, central difference. Of course, the central difference will be the most accurate one as compared to the forward or backward Euler, because it considers both the forward points as well as the backward points. So this is the most accurate one. Well, for the first derivative, what is the arrow associated with the first derivative? And that is related to the finite difference approximation. Okay, so the finite difference approximation is based on the Taylor expansion. Taylor expansion, which for fx plus h, fx plus h will be equals to fx plus h fx prime plus half h squared fx double prime plus 1 over 6 h cubed fx triple prime plus dot dot dot. And fx minus h equals to fx minus h fx prime plus half h squared fx double prime minus 1 over 6 h cubed fx triple prime plus dot dot dot. And we will see each finite difference method leading the arrow and why I say the central difference is the most accurate. Okay, so for the forward ruler, this is arrow analysis. So for the forward ruler, fx plus h minus fx divided by h, that is for the forward ruler, that is equals to, okay, that is equals to h fx. So fx minus fx divided by h will be h fx prime plus half h squared fx double prime plus 1 over 6 h cubed fx triple prime plus dot 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 divided by h, right? And that is fx prime plus 1 over half h fx double prime plus 1 over 6 h squared fx triple prime plus dot dot dot. So this is on the order of h, right? So this is on the order of h. Well, for the backward ruler, similar. We will do backward ruler is fx minus h divided by h, right? And that is equals to fx minus fx h is h fx prime minus half of h squared fx double prime plus 1 over 6 h cubed fx triple prime plus dot dot divided by h. That is fx prime minus 1 over 2 h fx double prime plus 1 over 6 h squared fx triple prime dot dot dot. Okay, and this is also the order is on the order of h. So the backward ruler and the forward ruler has similar arrow, which is on the order of h. Okay. Then how about the central difference? Okay, the central difference, central finite difference, which is fx plus h minus fx minus h divided by 2h, right? And you can use the equation, for example, before this is the fx minus fx minus h divided by 2h. What's that equals to? Let's just see from this equations. That should be equals to 2h fx prime plus 2 over 6 h cubed fx triple prime plus oh on the third, on the fourth, right? Or fifth. I think it's fifth. Then divide by 2h. And that is equals to fx prime plus 1 over 6 h squared fx triple prime plus O on the order of fourth, right? So you can see that this is on the arrow of h squared, which is significant accurate as compared to the forward ruler and the backward ruler, which is on the order of h here. So the central difference is a better choice for the derivative. Then if we use central finite difference for the finite difference method, how about the second order derivative? So this is for the first order derivative approximation. How about the second order derivative approximation? We just write here, you can do by yourself. So f double prime will be equals to fi minus 1 minus 2fi plus fi plus 1 divided by h squared plus on the order of h2. Okay, that is the arrow. And this is how we represent using the central difference approximation to represent the second order derivative. And in the printed note, we have more approximation you can adopt, but here we only introduce central difference, central finite difference to solve the finite difference method. Okay.